Our first set of notes for this class is going to cover functions, and I mentioned to you guys earlier that a lot of this is going to be a review. So if this isn't new to you, don't get too bored with it. Still pay attention. If this is new to you, then you definitely want to make sure you understand what we're doing, because this is all going to build up really rapidly when we towards us getting into the trigonometry of this course. So a lot of different things can be represented using functions. And a function just relates two different quantities together by some rule. And if we looked at this example right here, so this simple interest earned on $1,000 for a year is related to the annual interest rate by this formula. I equals 1,000 times R. So that is just a very basic function. We have an input, which is the rate. We have an output, which is the interest earned, and that's our function. And when we take these inputs and outputs, we are creating a relation between the x values and the y values. And here is our first definition for the class, and it's a very it's an abstract definition. It's very general, so it applies across all functions. But we have a function f from a set A to a set B is a relation that assigns each element x in set A exactly one element y that's in set B. So the set A is the domain or the inputs, and then the set B is the y values or the outputs. So if we imagine it kind of like a table of values. Okay, we could look at these x values as our set A and these y values as our set B. This set A only contains the numbers 1, 2, and 3, and then the set B only contains the numbers 4, 5, and 6. And we would map the x value to a y value that's in the set B. So this takes every element in set A, and it maps it to a value in set B. And that's all we're talking about with the relation. So for every x, there's a y output. All right, let me clear this off. And maybe this will help you, this example right here kind of help you understand that definition a little bit better. So we have this function represented by the ordered pairs. Here on the left, we have the time of day in this bubble, and then on the right we have the temperature in degrees Celsius. So at 1 p.m. the temperature is 9 degrees Celsius. At 2 p.m. the temperature is 13 degrees Celsius, and we can keep going down that list, matching the number in the time column to the value in the temperature column. And we can reorder these as ordered pairs as well. So this is what you see in the middle of your screen is called a map. And then what we see at the bottom of the screen would be the set of ordered pairs that are generated by that map. So the first one we have is 1 maps to 9, and then that's our first ordered pair down here at the bottom of the screen. So 1 p.m. maps to 9 degrees Celsius, 2 p.m. maps to 13 degrees Celsius, and we can go on through that list until we get down to the end where we have 6 p.m. maps to 10 degrees Celsius. So we generate XY outputs, or XY ordered pairs rather. And you should be very familiar with XY ordered pairs. So some characteristics of a function. Each element A has to be matched with an element in B. Some elements in B, however, may not be matched with an element in A. So some of your outputs may not align with an input that you have. Two or more elements in A may be matched with the same element in B, and an element in A cannot be matched with two different elements in B. So what we're talking about on number 4 there is if we have there we go, 3, 4, 5. So number 4 says an element A cannot be matched with two different elements in B. So I can have 1 map to 3, that's fine. I can have 2 map to 3, but I can't have 2 map to 3 and 4. Once that happens, this no longer represents a function, and the definition breaks down. All right. So there's 4 ways to represent functions. First one is verbally. We can just simply have a sentence that describes how the input variable is related to the output. Numerically, we would use a table or a list of ordered pairs. Graphically, we would just use a graph that shows the points on the coordinate plane. And then algebraically would just simply be some expression or equation that we're using to represent that function. To determine whether or not any given relation represents a function, you have to decide whether each input is matched with exactly one output. So this is very important. Each input must be matched with exactly one output. If any input is matched with two or more output values, then the relation is not a function. And that goes back to the little drawing I just did a second ago where I had 2 mapped to 3 and 4 at the same time. That is not a function in that case. So what we have here, we want to determine this first example for part A. We want to determine whether or not the relation represents y as a function of x. So in part A, it says the input value x is the number of representatives from a state, and the output value y is the number of senators. The description, this is a verbal description, it does describe y as a function of x. Regardless of the value of x, the value of y always happens to be 2. So each state has a number of representatives based upon their population size, but every state only has 2 senators. So it doesn't matter how many representatives we have. So let's make just a quick diagram here. We have the representatives over in this column, and then we have senators on this column. Well, this number can only be 2. Every state always has 2 representatives or 2 senators, regardless of if they have 10 representatives, 3 representatives, 5, 8. It doesn't matter. If a state has 10 representatives, they still have 2 senators. If they have 3 representatives, they have 2 senators. All right, just like that. So every input in the left-hand column has 1 output. It just happens to be the same output in this case every time. On on part B, it wants to know whether or not this table represents a function. So 2 maps to 11, 2 maps to 10, 3 maps to 8, 4 maps to 5, and 5 maps to 1. The question is this a function? At first glance, if we just look at the number of lines we have going across from left to right, we might say yes. The problem arises right here. They use the same input twice, and in both cases we have a different output. So 2 actually maps to 10 and 11. And once we have one input that goes to 2 different outputs, we have lost the definition or the criteria of this being a function. So this is not a function. And then finally, our last one is a graphical representation. We want to determine whether or not this represents a function. And we look along the x-axis first. And at x equals 2, we have this y value of 3. At x equals 0, we have a y value, x equals 1, we have a y value of 0. At x equals 0, we have a y value of negative 1. At x equals negative 1, we have a y value of 0. And then at x equals negative 2, we have a y value of 3. So if we put that in a table, we have negative 2, negative 1, 0, 1, and 2. And our outputs, we have negative 1, 0, and 3. So negative 2 maps to 3, negative 1 maps to 0, 0 maps to negative 1, 1 maps to 0, and 2 maps to 3. Okay, so we have, in each input, there's only one line coming from that map over to the outputs. We can have multiple lines lining up with a single output, just not the other way around. We can't have multiple lines in a map lining up with a single input. So this graph does represent a function. So sometimes we have equations, and we have to look at those equations and determine whether or not they represent a function of x. So does every input generate only one output? So for the first one, let's solve this equation for y. And we'll solve that for y by subtracting x squared from both sides. And what this means is, can we put in, for every input, so any x value we choose, we are going to get a distinct single y value. So it doesn't matter what we put in here. Y equals 1 minus x squared. Does not matter what we put into that function. It will always generate a individual y value. I can't put in any x value and generate multiple y values. So if I put in 2, I'm going to get negative 3. 1 minus 4 is negative 3. No x value will generate more than one y value. If we look at part B, again, we want to solve this for y. So the first thing we're going to do is add x to both sides. And then take the square root of both sides. And remember, when you take a square root, you have a plus and a minus for the square root. In this case, any input for x will generate 2 outputs for y every single time. So let's just try a simple case of x equals 0. If x equals 0, I get y is equal to plus or minus the square root of 1 plus 0, which is going to be plus or minus the square root of 1, which is plus or minus 1. So my two outputs are negative 1 and positive 1. My single input of 0 has generated 2 outputs of negative 1 and positive 1. So anytime you end up with a square root like that over an entire expression on the right, you are going to have the situation where this is not a function because you get 2 outputs for 1 input. Function notation. You guys have probably seen this before. Instead of using y, we're using f of x. So if you need to, you can rewrite it as y equals. If that f of x is confusing you, just make sure that you understand the notation and that you use the notation as you work through any of your problems. But it is very important to understand that you can kind of interchange those two, y equals f of x. It's just simply read as, if we look at this one here in the middle of the screen, the function of x is equal to 3 minus 2x. So whatever value we put in for x into the function notation is what we substitute into our equation. If we looked at f of negative 1, that's this line right here. I replace x with negative 1 and evaluate the expression. So what that would mean is we have 3 minus 2, replace x with negative 1, so we get 3 plus 2 equals 5. So the function notation gives you an evaluation point sometimes for the expression or the equation that you're looking at. Some other examples, we don't always have to use x. We can have a function of t, we could have g of s. It just is a matter of the problem that you're working with. So like that middle one there, f of t, that could be a function of time. G of s, I don't know, it could be grams per second. It could be a chemistry problem, so you could have grams per second, and so that notation would make more sense in that context rather than using f of x every time. So for example 3, we're actually just going to evaluate some simple functions. We're using the g of x equals negative x squared plus 4x plus 1, and for part A we're substituting 2 in for x. So we have g of 2 is equal to negative quantity 2 squared plus 4 times 2 plus 1. And I'm going to stop right here for a minute. Anytime you all make a substitution into a given equation, I highly recommend you put that substitution in parentheses, especially if you're going to use a calculator to try to solve it. Because if you don't use the parentheses, a lot of times when you deal with that negative that we have right here on the negative x squared, the calculator is not going to read that correctly when you type it in. So the parentheses will make a big difference in your solution. So what we get here is 2 squared is 4. We have that negative out in front. 2 times 4 is 8. And then when we simplify this, negative 4 plus 8 is 4. 4 plus 1 is 5. For part B, we're just evaluating the expression at another variable. In this case, t. It could be time, whatever the case might be. and when we simplify that, we do end up with negative t squared plus 4t plus 1. And then our last one is we're evaluating this given equation at an expression. So we have g of x plus 2. And every instance of x in our equation, we replace it with x plus 2. And then we simplify. So first we have the x plus 2 quantity squared. That expands to x squared plus 4x plus 4. And we have 4x plus 8. Oh, I'm running out of room. And there's going to be a plus 1. If I can get it to fit. Plus 1. So when I simplify this, I have negative x squared minus 4x minus 4. That's just from distributing this negative through the parentheses. Plus 4x plus 8 plus 1. And then I'll combine like terms. So I get negative x squared. Negative 4x plus 4x is 0. Negative 4 plus 8 is 4. 4 plus 1 is 5. And so I get g of x plus 2 reduces to negative x squared plus 5. Sometimes we have a piecewise defined function. So this function is defined by multiple different equations, and they have different parameters associated with those equations. So if you look at the one here on example 4, it says f of x is equal to x squared plus 1 given that x is less than 0. So x has to be strictly less than 0. When that's the case, we use the x squared plus 1. The other piece of this piecewise function is f of x is equal to x minus 1 when x is greater than or equal to 0. So anytime you have an x value of 0 or greater than 0, you would use the x minus 1 portion of this function. So we want to evaluate this function using x values of negative 1, 0, and 1. So if I evaluate f of negative 1, negative 1 is strictly less than 0, so I'm going to use the x squared plus 1. I'll replace x with negative 1, and then I evaluate negative 1 squared is 1, 1 plus 1 is 2. So f of negative 1 is 2. If I evaluate the same function at 0, when x is equal to 0, we would use the second line because this second line is only defined when x is greater than or equal to 0. So then I substitute 0 in for x, and 0 minus 1 is negative 1. And then the last one is when when x is equal to 1. Again, we're going to use that second line because that second line is defined when x is greater than or equal to 0. 1 is definitely greater than 0. So we just substitute in our value for x. 1 minus 1 is 0. And there we've evaluated this function at multiple points across its domain, and we've come up with these solutions. The domain of a function is the set of all inputs that are valid for that particular function. So in the case of example 5, we're looking at what are the inputs of this. For part A, for example, we're looking at what are the inputs for that set. That set is only defined by these 4 ordered pairs. There's nothing else to that set. So all we have to do is make a list, and I use this notation right here, so I use the set notation. X, and then this vertical line means such that, or sorry, yeah, I can still use this, such that x is equal to negative 3, negative 1, 0, and 2. Or you can use the set notation. The domain is equal to negative 3, negative 1, 0, and 2. And if you're just lazy, you can write D is equal to negative 3, negative 1, 0, and 2. I would prefer you use one of these two notations just for the sake of being consistent throughout the course. For part B, it says find the domain of this function. Whenever you're looking for the domain of a rational expression, take the denominator, And we can say that the denominator is not equal to 0. We subtract 5 from both sides, and we get x is not equal to negative 5. And what this shows us is the set of values that we have to eliminate from the domain. So at the very beginning, at the outset of this problem, the domain currently is all real numbers. When we figure out what numbers don't apply to the denominator, we eliminate those from the denominator or from the domain, and now we have the remaining domain of this function. So again, the set notation domain is equal to, we have x such that x is not equal to negative 5. So that would imply that it's all real numbers with the exception of negative 5. Or you could just say x not equal to negative 5. And then the third one, you can use interval notation. We have negative infinity to negative 5 with parentheses because we're not including negative 5. Union negative 5 to infinity. So if you've not seen the interval notation before, I'm hoping that you have, but if you have not, then that's what it's going to look like. You're going to have the parentheticals or sometimes square brackets around the values. It just depends. And then for part C, I didn't label it part C, and I forgot to also mention that this is the volume of a sphere. So when we look at that, this is defining the volume of a sphere as 4/3 pi times radius cubed. On its own, that equation could have any r value that we wanted to put into it. It could have negative 1,000. It could have positive 1,000. It doesn't matter. Any number is going to work. However, because when we define this as the volume of a sphere we know cannot have a radius of negative values, and it also can't have a radius of 0. If r was 0, then the volume is 0, and that's not a sphere. So we are restricting this domain just in the context of the problem. It's going to be that all r greater than 0. If you did the set notation, we would have r such that r is greater than 0. Interval notation would be 0 to positive infinity. So whichever notation you prefer, go ahead and use that. With example 6, it's going to be a more concrete example here. It says that we work in the marketing department of a soft drink company, experimenting with a new can for iced tea that is slightly narrower and taller than a standard can. For the experimental can, the ratio of the height to the radius is, what did I write there? I'm sorry, I had to pause for a minute there because I even confused myself for a second. It should just say the ratio of the height to the radius is 4. And then what we have here in the parentheses is just that example. It's the height over the radius is equal to 4. For part A, it says write the volume of the can as a function of the radius r. So the volume will be expressed as of the can. Let me kind of do a terrible drawing here. So here's our can. And to find the volume of a cylinder, we have two circular surfaces, the top and the bottom. And the area of any circle is pi r squared. And then we have to multiply that by 2 because we have 2 of them. And then we also have the height. Sorry, not 2. You don't multiply by 2. Forgive me. Pi r squared, which is the area of the circle, times the height is going to give you the volume of the cylinder. So we have volume, and we're going to express this as a function. So volume, V of r, volume as a function of the radius, is equal to pi r squared h. And you may remember that equation from geometry. And we take this h, and we want to write this whole function in terms of r. So what we have up here, where h over r is equal to 4, if I solve that for h, that means I multiply both sides by r, and I get h is equal to 4r. So if I replace h in this equation that I'm writing down here with 4r, I get pi times 4r cubed. Clean this up a little bit. 4 pi r cubed. So that's the volume of the can as a function of the radius. Part B wants us to write the volume of the can as a function of the height. So again, if I take this h over r equals 4, and this time I'm going to solve it for r because I'm trying to eliminate, or I'm trying to just write everything in terms of h, so I need to get rid of the variable r. So I need to solve this for r, and I would get r is equal to h over 4 when I simplify that. So for part B, I have volume as a function of the radius, pi r squared h. We always start at the same point, but now I'm replacing r with h over 4 because I'm trying to eliminate the radius variable and rewrite this in terms of h only. And then that gives me pi times h squared over 16 times h. Multiply everything through by h, and I get h cubed over 16 pi as my volume in terms of h, and I should have written that as volume as defined by h rather than r. Example 7, baseball is hit at a point 3 feet above the ground at a velocity of 100 feet per second at an angle of 45 degrees. The path of the baseball is given by the function f of x equals negative 0.0032 x squared plus x plus 3, where y and x are measured in feet. Will the baseball clear a 10-foot fence located 300 feet from home plate? So all that means is we're substituting in values. The value for x is 300 feet. That's how far the baseball needs to travel. So let's evaluate this function. F of 300 equals negative 0.0032, and then we put in 300 squared plus 300 plus x. And we're going to use, let's use a calculator to simplify that, if I can get it to pull up here. All right. We want to go to desmos.com. And I need to type this in. I have negative 0.0032 parentheses. I'm replacing the x with 300, squaring that quantity, plus 300 plus 3. And I get the result of 15. So going back to our notes, when we simplify this expression, we get that f of 300 is equal to 15 feet. So the question says, will the baseball clear a 10-foot fence if that fence is 300 feet from home plate? Well, when the ball is 300 feet from home plate, it's 15 feet in the air. So it will clear a 10-foot fence. And there we go. So the ball will clear the 10-foot fence if it's 300 feet away. Our next example, the volume, or number, V, in thousands of alternative fueled vehicles in the United States increased in a linear pattern from 1995 to 1999. Then in 2000, the number of vehicles took a jump, and until 2002, increased in a different linear pattern. These two patterns can be approximated by the function that's given here, this piecewise function. So when time is between 5 and 9 years, we use the first equation. When our time constraint is between 10 and 12 years, we will use the second equation. So t represents the year. T equals 5 is 1995. So if you think about it, so we have 5 is 1995. That means 6 is 1996. And we can keep going on. When we get to 10, that's going to be the year 2000. 12 would correspond to the year 2002. So use the function to approximate the number of alternative fueled vehicles for each year from 1995 to 2002. Now I'm not going to go through and type this in for every single year, but what we have is we would evaluate V of 5, V of 6, V of 7. And the reason I'm typing is I want to save you guys a monumentally long video. So I would use 18.08 T plus 155.3, and I would just substitute in 5, 6, 7, 8, and 9 and evaluate each time, and that would tell me how many cars approximately were on the alternative fuel cars were on the road in 1995, 96, 97, 98, 99. Then when I jump to the year 2000, I'm going to use V of 10, and then V of 11, and V of 12. So there's 2000, 2001, 2002, and I will use the expression 38.02 T plus 10.2. And again, evaluate, and then I'll have the solution for those 3 years. Difference quotients are the ones that frustrate many students. Hopefully, I'm trying to get better at maybe explaining them. I don't know if it's my fault that it becomes an issue for some people. But the difference quotient will pop up a lot when you take calculus. At the very beginning of your calculus course, when you're learning how to do derivatives, you will see the difference quotient until your eyes are bleeding. But for this one of the basic definitions is going to be this ratio. It's f of x plus h minus f of x all over h. H cannot be 0 because then the function is undefined. This ratio is called the difference quotient, and it's the fundamental definition to computing derivatives in calculus. But you have to be able to handle the algebra. So I'm going to break this down into a couple of different components. We have this piece right here, which is f of x plus h. We have this piece, which is just simply f of x. And then we have our denominator, which is just h. So let's look at just what I've highlighted there in purple. That's f of x plus h. So I'm going to take my function, and I'm going to replace x with x plus h. That's what we were doing at the beginning when we looked at the function notation. So this is going to give me x plus h quantity squared minus 4 times x plus h plus 7. The expansion of this x plus h quantity squared, remember, is the same as x plus h times x plus h, and then you can use the FOIL method if that's what you want to use, or the binomial distribution, or whatever you want to call it. But we have x times x is x squared, x times h is xh, h times x, we have xh again, and then h times h is h squared. So this simplifies to x squared plus 2xh plus h squared. Now that's just this x plus h quantity squared. Now I'm going to distribute the negative 4 through the x plus h, so I get minus 4x minus 4h plus 7. So the parentheses also help you, especially on this term, to make sure that you distribute that negative to each one of the terms. A lot of times I see people take the negative 4 to the x, and then they just simply say positive 4h. For whatever reason, they ignore the negative. So let's simplify this. X squared, I'm going to rewrite this term with our variable at the end, so it's 2hx plus h squared. Actually, that doesn't simplify any further. That is it. So minus 4x minus 4h plus 7. Okay, so that's the purple that we put in brackets right here. That's the f of x plus h. The f of x in red is just the original function. Okay, so here's where you want to be careful with your negatives and things like that. So let's go ahead and write the f of x plus h, and I'll use the same color still. So we have x squared minus 2x or 2hx plus h squared minus 4x minus 4h plus 7. And then that's going to be minus the original function, x squared minus 4x plus 7. And again, I put that in parentheses because you want to be sure to distribute the negative through the entire function. And then when we simplify that, I'm going to stick with black now. The numerator is x squared minus 2hx plus h squared minus 4x minus 4h plus 7. Distribute the negative through the parentheses. Minus x squared plus 4x minus 7 all over h. And we'll clean that up by simplifying. The x squareds will cancel. The positive 7, the negative 7 will cancel. The negative 4h, the positive 4x will cancel. And what we are left with now is negative 2hx plus h squared minus 4h all over h. And these h's will cancel, and we're left with negative 2x plus h minus 4. Sorry I ran out of room and tried to cram all that in. But it's just a matter of being very cautious with the algebra. The difference quotient it's not bad. It's just one of those things you have to be really, really careful with the algebra to make sure you do the right steps. That should conclude the notes. Yeah, it does. Your homework are these 21 problems. And I may, when I post this, feel generous and reduce it, how many problems I want you to do. Actually, I am feeling generous, and I will reduce it. So when I post this on Classroom, you won't have to do all 21 problems, but you'll do a good portion of them to make sure you understand what we covered today in class. Hope you guys have a great evening, and I'll be talking to you soon.